Hi everyone, this is the third and final instalment of videos on simple harmonic oscillators, SHM, and this is looking at the energy stored in a simple harmonic oscillator, the maths behind it, the consequences of it, and the uses as well. So what I'd like to do is just pick up this simple system of a mass on a spring, and I've drawn it sideways, horizontally, because we don't want to consider gravity yet. And this is obviously going to move from its equilibrium position, and it's going to move back and forth by a certain displacement x. Now, what do we know about how that oscillator moves? Well, we know that at certain points in its oscillation, here for instance, and here, its velocity is going to equal 0 at those points, because it's stopped its turning around. It has a maximum acceleration, it has a maximum displacement, but 0 velocity. We also know in the middle we have a maximum velocity, because that's where it's moving through with 0 acceleration, and yeah, I suppose intuitively we say it's moving through there with its maximum velocity, because there's no 0 acceleration. It's picked up the most amount of speed it can from this part where it's slowest, and then it's flying through the middle and then slowly being deaccelerated until it gets to the edge. Good. Similarly, we ought to say that we're at a maximum displacement at the edges, and whether that's a minimum, but it's still a maximum. And then in the middle, of course, we have a 0. So these 3 points. Good. And we know that we're going to get an exchange of energies. We know there's going to be an elastic potential energy from the spring, and we know there's also going to be kinetic energy from the movement of the mass. And there's going to be exchange between these two. Sometimes it's going to be kinetic, sometimes it's going to be elastic potential energy as it moves back and forth between the two. I think I'll add here a video, if I can, just to show you how that works, to give us a sense of what's going on. Let me quickly find it. Only part of a video which I'm going to use next, in the next part of this video, a bit more extensively. Good, here is the video. I'll just shrink it a little bit. No, I'll zoom it up so you can see it, and then I'll shrink it afterwards. Now what it's showing in effect is it's showing, I have here my simple harmonic oscillator, a pendulum, and on this side it's showing the kinetic energy, the potential energy, and the total energy. It also has the thermal energy, which takes place when I introduce friction, because we know that this system will slowly, the decay will decrease to nothing because it's going to go to thermal energy. But for the meanwhile, I'm interested in these two and how they react with that. Take a look and see what we can do. I'll talk over it at the same time. So I'll just hit go on this. Here we have, right, I've got it moving in slow motion at the moment. I'm going to zoom this up so you can see a little bit more easily what's taking place. So at a maximum displacement, the amplitude, we have a maximum potential energy that's going on. It's not moving, but it's maximum. And then we have the maximum kinetic energy when it's moving through the middle. Hopefully we will see that happen again. And if not, I'll rerun it again. So we've got moments of maximum potential energy when it's not moving, maximum amplitude. Then we've got maximum kinetic energy in the middle as it goes through the equilibrium position. And the total energy you'll see is unaffected. It might have a different exchange of whether that's kinetic or potential, but it's at a fixed value. Now that's really interesting, and hopefully I'm going to show you the maths that will support that idea. So let me shrink this down again, move that out of the way, and talk about our respective energies. The elastic potential energy, is going to be a half kx squared, and the kinetic energy, is a half mv squared. Now, from the work in previous videos, x is a cosine omega t. I've forgotten about I haven't bothered putting in the eta there because let's just imagine it's starting from, we don't need a phase shift in this, and it's starting from the right point. Hold on, that might have been easier if I just undid. There we go. And if I add into there the velocity, hold on, wait a minute, sorry. That's the kinetic energy here. And this is the elastic potential energy here. So if I add in the velocity, that's going to give me, because remember I differentiated this with respect to time, minus omega A sine omega t. So what I need to do is just substitute these into these equations and see what I come out with as an answer. So let me first of all write down the, let's move it all out of the way. Elastic potential energy is going to be a half k x squared, which is a half k a cosine omega t all squared. My elastic, that's my potential energy. My kinetic energy, let's just call it EK, is going to be a half mv squared, which is a half m omega a sine omega t all squared. There is a minus in there as well, but that will drop out when we square it. And this gives me a half k a cosine squared omega t squared, and this gives me a half m omega squared a squared sine squared omega t. Now, the total energy is merely going to be the addition of the two, because those are the only two systems I've got going on. And if I add the two of these together, that's going to give me a half k a squared cosine omega t plus a half m omega squared a squared sine omega squared omega t. Now, what I hope you can sort of see here is that I've got a cosine squared, and a sine squared. And if I'm adding those two together, I hope you understand I hope you know the identity of, I'll just put it in blue here, cosine squared theta plus sine squared theta gives us 1. So if I can try and factorize these two out, then that will make life a lot easier. And you can see that we're starting to move towards our constant value. So what is my value for k? Another blue here. We've said before that omega squared is k over m for a mass on a spring system. So therefore, k is going to equal omega squared m. Let's substitute that into there. That's going to give me, therefore, a half omega squared m a squared cosine omega t squared plus a half m omega squared a squared sine squared omega t. Okay, this is now starting to look pretty good. A half omega squared a squared m, open brackets, sine squared omega t. Brilliant. A lot of maths there, but what this all tends to is 1, and that gives me the total energy is a half omega squared m a squared, which is, in effect, constant. And that's what we saw in the previous video, and if I need to jump back at all so you can see this, the previous video showed exactly that, in that we had a constant value for energy throughout the entire oscillation. And I know this is a pendulum, not a mass on a spring, but we know they're both simple harmonic oscillators. A total constant value of the total energy, though these two oscillate, moving between kinetic and potential. Okay, so what does that look like, therefore, in terms of, let's take a look at where the rest of my text is. What does that look like in terms of a graph? Well, I'm hoping that you're familiar with a cosine squared graph looks like and a sine squared graph looks like, because we merely have the addition of those two in a graph. I think it's easier if I just drop a graph in so you can see. Let's I'm just quickly finding one for you, and nearly there. Here we go. Wonderful, just positioning that so you can see it. Let's talk through this. Okay, we've got our energy, half Ka squared. I mean, don't worry about the way in which they've written it, but we have our total energy sitting at the top here. And we definitely know that these are respectively our cosine squared graph, and this one is our sine squared graph. And you can see how they exchange, giving our total energy to be constant all the time. Now they've placed this in terms of time periods, but we also might want to put it in terms of radians. That would be a quarter of an oscillation. This would be half an oscillation, 3/4 of an oscillation, and a full oscillation, if you like. And just to give you this sense of how you make those up, if this is the velocity, then in actual fact, why don't I just add this in to make so you can see the let me just get this absolutely right. That's right. The squared relationship would be, though badly drawn, cosine squared, sine squared would look like that. And if this were the cosine graph, then cosine squared would look something like this, though badly drawn. And those are what you see in here. Good. I suppose I'll show you how you might have to answer a question on something like this. You might be asked a question that would say something along the lines of, let's imagine we had an object that had a 5 kilogram, had a mass of 5 kilograms, and it was behaving according to this equation: 10 cosine 100t, and you had to work out first of all the total energy, and for part B you had to work out the potential energy and the kinetic energy at t equals 0. And then thirdly, you needed to work out the potential energy and the kinetic energy at t equals pi over 200 seconds. So if you think you know how to do it, hit pause and give it a go. Otherwise, here comes the answers. Okay, so let's just, you need to take some, you need to understand a little bit better what's going on with this equation. We know that that part is the amplitude, and we know that this part is omega. So if our total energy from the previous theory is a half m omega squared a squared, then using those numbers we have a half, 5 kilograms we're given, 100 squared we've found out from the equation, and 10 squared from the previous one. We should be able to work out the answer. So let's put those values in, and that brings us up to something like 2.5 times 10 to the 6 joules. That's a considerable amount, and actually, I suppose looking more carefully, that probably ought to be something in centimetres. And if we were to redo it in centimetres, then that comes out at 250 odd joules rather than that before, because a 10 meter amplitude is considerable. But there we go, it depends how they define it. What about the potential energy and the kinetic energy? Well, the potential energy at t equals 0, well, that is going to be equal to, let's just remind ourselves of what's happening. X is going to be 10 cos of 0. Once you multiply it by through, which gives us 10. So the potential energy is at a maximum. And what about the kinetic energy? T equals 0. That's going to be velocity, which is 10 sine. We've got an omega at the front as well, of 0, which equals 0. So the kinetic energy is going to be at a minimum. So I'd say the kinetic energy is at 0. And the potential energy is that which the total energy is, because all of the contribution comes from that. Okay, and finally, what happens at t is pi over 200 seconds? Well, that looks a bit complicated, but omega t is therefore going to equal 100 pi over 200 seconds, which gives us pi over 2. And we know that the potential energy, which is obviously dependent on cosine, we know cosine pi over 2 is going to equal 0. And the kinetic energy, it's obviously a sine function of pi over 2, is going to equal 1, which is at a max. So if I just translate those, potential energy is going to be equal to 0, whereas the kinetic energy is going to be equal to a max, which is equal to the total energy of the system. Good. Right, I hope that makes sense. Now there is one more situation we need to talk through, which is in the textbook. So let me just a new page to work this one through for you. It's exactly the same as before, but you've layered in more mathematics here. So let me just talk you through this one. We have a mass on a system, on a spring, that's actually vertical. So we have to consider gravity. Well, not gravity, the fact that this extends beyond its equilibrium point. Let me try and explain that better. I did that very badly. We know that it will extend with said mass to a point which I'd regard as L. That's right. So it's going to sit at a certain length, L. And then it will be displaced beyond that, and that displacement will be at an amplitude A, and it will subsequently move about between those points in simple harmonic motion. But it has had an extension that's taken place before it. Now, we know the spring constant is K, we know the mass is M, we know that at t equals 0, the load is released, and we're asked to sketch a graph of the potential energy of the system. Now, let's just tell you why you can't just jump to previous knowledge here. Because people would say, okay, I've got an idea of this. We know that the potential energy of the system is a cosine squared graph, and so therefore I've got something that does this. But that's not the case, because this is assuming that we've got a 0 point potential energy with respect to time, and we haven't. It's actually moving about a point which is at its natural extension length, not about the 0 point natural extension length. So if anything, what's going to happen is you have to take out this axis. This axis is going to have to move down here somewhere, And this is what it's going to have to do. So how do we work that out carefully? Well, let's just go through the maths here. Let's say the amplitude, or the position L, is going to be mg over k. In other words, it's the weight divided by k, because it's the force divided by the spring constant. So we know how far it's going to extend. We know that, and that we could describe, it's the amplitude. We know that for x, the equation of this is a cosine omega t, which now we have an expression for mg over k cosine omega t. And of course we know that this system is a mass on a spring. And for mass on a spring, omega squared is k over m. We've done that numerous times. Now the energy of this system, because we're talking about the GPE, is going to equal mgh, which we've written as mgx, its displacement, which is mg by mg over k cosine omega t, which is m squared g squared over k cosine omega t. Okay, now the EP, the elastic potential energy in the system, is going to be a half k x squared. Now how do we relate the amplitude to the extension? How do we know how much is being extended in terms of that original length? Well, we can say a half k a minus x all squared is the extension that we're dealing with. Because it's the difference between that which is extended by its amplitude to, so we're looking at the difference between its amplitude here and its position, wherever that might be, a minus x. Okay, just bear with us, this is all going to drop out in a moment. So that gives us a half k. Remember again, we have mg over k gives us our amplitude, and mg over k cosine omega t gives us our position at any one moment. Square that up. That gives us a half k m squared g squared over k squared, open brackets, 1 minus cosine omega t squared. And those cancel, giving me a half m squared g squared over k, 1 minus cosine omega t squared. So therefore the total potential energy is the addition of these two factors. That would be a half m squared g squared over k, which is the 1 minus the cosine omega t all squared, and add to that the GPE, which was m squared g squared over k cosine omega t. Now we need to expand these brackets and then give this an extra, and then expand this bracket and then get a common factor between these two. Of course this is a half, so this is going to go to 2 lots of cosine omega t. Let's work that through. Gives us a half m squared g squared over k, 1 minus 2 cos omega t. Remember, it's 2 lots of the addition of the multiple of those two, plus cosine squared omega t, plus, let's get a common factor in this, let's get a half m squared g squared over k, 2 lots of cosine omega t, gives us a half m squared g squared over k, 2 cosine omega t, I'm taking this one first, plus 1 minus 2 cosine omega t, plus cosine squared omega t. Okay, we can see these two drop out quite neatly, leaving us with a half m squared g squared over k, 1 plus cosine squared omega t. So now if we draw that in terms of graph, t and EP, what I'm going to get is I'm going to get, as we described, a cosine squared graph. But it's been displaced by that 1, and not just the 1, well I mean 1, but a factor of 1, which is a half m squared g squared over k. And that gives me at the top here m squared g squared over k. And how did I work out the top value? Well, the brackets here at a maximum equal 2. 1 plus cosine squared omega squared, which the maximum equals 1. So that factorizes, that brings it to 2. And 2 lots of a half m squared g squared over k gives me m squared g squared over k, which is what I've got on that side. Now that's a long problem, which in effect has just demonstrated why we've got this movement from the origin. But I hope one that you'll follow through and you'll appreciate what's going on. Okay, let's move on to the next bit. Now, with this part, of the video, we're going to change tack a little and look at damped oscillations. Let me just write that in first. And I want to draw attention back to this video, this FET video, excellent website. I've mentioned it before. But let's just take a look at these oscillations that are taking place at the moment. Now, what happens here is we move this to a certain position, release it, and then it oscillates, as you'd imagine, and slowly it would go back to 0. Now, what I've done is I've set the friction to 0, so now it will keep going back and forth, back and forth, back and forth. And what I want to try and describe to you here is that is what we call its natural frequency, or indeed it's undergoing a free oscillation. You can see here with the red one, that has a free oscillation, which has a different time period because it have different lengths and different masses for each of them. You can see one catching up with the other. But you need to appreciate there that that's what it would do naturally. And once I've increased the friction, then those oscillations diminish. But the oscillations don't diminish at a change the time period. Once again, we're familiar with this graph here. We've been looking at how the energy changes, but interestingly, this thermal energy is increasing. What happens there is that the friction, due to air in this instance, means that some of the energies will move towards thermal oscillation, the thermal energies. And of course, when I remove the friction, it constantly moves back and forth and we've got no energy loss. Let's go really slowly there. So you can see, well, I did this before, so you can see when those energy exchanges happen. But the first essential point I want to make from this, and I think I'll just pause the video there, because you've probably seen enough, is that we have what's called free oscillations. And free oscillations are, I suppose, or part of the term which I've taken from the textbook says that if there are no external driving forces, a system undergoes
free oscillations. Now, that's important. In the first instance, the only driving force I put into it was moved it to this position, then I released. But that's a free oscillation, and that is important as we move ahead. Now, this is going to be a lot of videos in here because they're critical in appreciating what we're trying to understand. And the next one will be, it's actually taken as a YouTube clip. Hopefully it won't take long to compress. Hopefully I'll accredit all of these YouTube authors, so you can turn to their videos if you want to. But here's the next one, and this one is showing you a mass on a spring. Now this mass on a spring is going to move back and forth, and what's nice is that we've got a weight there. I suppose this is friction. Well, there's a bit of friction there. That's what's causing this for the oscillations to diminish. And this is quite interesting, the restoring force. This is a compressive and extensive spring, and then you've got the energies as well. It's really good. But let's press play and see what we note here. Importantly, this is like a ticker timer. It shows the positions of where things are. And you can see we have a nice oscillatory motion here, a nice cosine or sine, depending on on which point we're starting at in the cycle. And I've skipped this forward just to look at how this is diminishing. It is diminishing until it goes to zero, because we're going to have eventually all the energy from the friction dissipate into heat and diminish. So therefore, and of course this is YAR physics animation, credit that because it's a very good animation. But why I wanted to show you that was because, hold on, it puts more context to this type of graph. This type of graph here. And what I've done is I've taken this straight out of the textbook to show you. And it's effectively showing that oscillatory motion. In actual fact, wait, hold on a minute. If I did that, it shows it almost identically what took place. You've got the oscillatory motion, but also it's diminishing, and it's diminishing exponentially. And I'll explain what that means in a minute. But let me just rotate that the right way around again so we can see what's going on here. There we go. So, let's start writing on this. Now, we've got this part of the graph here, which has the form x equals a cosine omega t. Let's find another colour to see if we can write on that better. Yeah, there we go. A cosine omega t, which you're familiar with. The black part here, a cosine omega t. In actual fact, you'll be able to work out exactly what those values are as well, because you know that this is the amplitude, which is 10 centimeters, and you know that omega is 2 pi divided by the time frequency. And what is the time period? And what is the period here? Well, let's just take this point there, and one full oscillation to this point here gives us 2 seconds. So 2 pi over 2 gives us pi. So if I wanted to write the equation, x is I know what a is now, 10 cosine pi t. There's no eta required because we're going from cosine. Epsilon, sorry, because we're going from cosine. But what we now need to look at is this here, this dotted line. Now we describe this as exponential, and the exponential function looks like this. And what it's saying is we start with an initial amplitude of 10, and then subsequently later on we have an amplitude which is diminished. And it's diminished to, in this case, if each one of these is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, this is diminished to 5.5. Let me write that in, 5.5. The next one's diminished to, what have we got here? We've got, sorry, what am I talking about? That's not 5.5, hold on. Brain meltdown. let me just draw this in so we're absolutely sure. That is 6, 7, 8, 9, 10. Sorry, yeah, so it is 5.5, sorry. And now here, that's 4, 3, 2, 1. So this point here is 3. The next point here, more or less, I know we're slightly out here, but let's just say that's 1.5. And this point here, I will make an assumption it's between the two, so I'd say that's 0.75. So an initial amplitude of 10 reduces to the next amplitude of 5.5, 3, 1.5, 0.75. What we need to work out is whether it really is exponential. And what exponential says is exponential saying that the ratio of, let's say, the A1, A2, A3, A4, the ratio of A1 to A0 should be the same as A1 over A2. In other words, the amount by which it's diminishing by is the same factor each time. Is this amount diminished the same as that it's diminished by? We can quite easily see whether that's the case. Should we just throw some numbers in and see what happens? Let's say 10 over 5.5 gives us, and 5.5 over 3 gives us. Let's see what the values of those are. This gives us 1.82, and this one gives us about 1.83, so they're approximately the same. So I'd say it is exponential if that's the factor by which we're going by. Of course, the steepness of this is determined by this factor lambda. And there are ways in which we can work this out graphically that I'll show you a little bit later on. Or indeed, we could work it out via substitution. Let's just go for substitution in the short term and see what we have. We could have, so I'm going to jump from there to here. And I'm going to say that x is a0 e to the minus lambda t. The time period between 10 and 5.5 is 10 e to the minus lambda by 2. That's 2 seconds, milliseconds that's occurred by. Now I can either change to milli, or I can just factor in that into lambda by saying lambda is a function which is milliseconds. So let's just, for ease, let me just keep it in milliseconds. Similarly, I'll keep it in centimeters. So therefore 5.5 divided by 10 is e to the minus lambda 2. ln 5.5 over 10 gives me minus lambda 2. Minus ln 5.5 over 10 by half gives me lambda, which is, in effect, it's giving me something like 0.3 once I've rounded it. Excellent. So that gives me, oh, let me just write it in full. Why not write it in full so you can see the entirety of the equation? So we would have, and I'm just going to jump back so I can see the entire thing. And we'll say that the entire function now is 10 e to the minus 0.3t cosine of pi t. There is my entire function. So now at any stage, I'll be able to work out where the function is, whether it's just here after t equals 1.8. I'd be able to work out that height if I substitute into this equation. Good. Now, we need to look at a few more specific examples of this type of decay. Now I've just jumped straight and I've loaded the next video over the top. I'm just going to move this down out of the way a bit. Oops. In that, here we go. Now, nearly there. Hold just a bit of repositioning. and then we'll take a look at what's going on here. Now I'd like you to take a look at these three instances of damping, and it's by XM demo. And we've got these three conditions: critical, overdamped, critical, underdamped, and a collage of them. Take a look at the next one, critically damped, and then an overdamped situation, and then we've got a collage of all of them. I'm just going to roll back so you can see those three again. A little bit of explanation needed as well. Okay, first of all, duly noted, excellent video by XM Demo. And we're looking at overdamped. Now, overdamped in effect means, underdamped means that it will keep on oscillating. Critically damped means that the system will return to equilibrium as quickly as possible, that's this one. And overdamped means it returns to equilibrium without oscillating. So therefore, let's press play and look at those three instances again. So this one is underdamped. It's just moving around all the time, bouncing back and forth. Very little damping there. This one moves back very fast to the equilibrium, but doesn't bounce back and forth beyond. Overdamped does do exactly the same, but just very, very much slower. And then we've got a collage of all of them, but not that we want to worry too much about that. Let me jump back to the beginning bit then, so you can see those three. Now, this is really important for situations like for physical engineering, physical systems in which you don't want oscillations to keep going all the time. The critically damped one is the one that's really useful, because you probably want to critically damp most situations, like suspension in cars, in bikes. If you want to just take out damping without, and I suppose you might say to yourself, well, surely overdamped's just as good, but overdamp means that it's so resistive to oscillations that actually all of that energy will be transmitted to the person in the car. That person, if you're going over a speed bump, you get jolted around, but what you want really is you want the wheels to be jolted and the suspension to take up the bump without you feeling it, hence critically damped. Again, it's probably best if we look at a graph of that situation to understand what's going on. It's probably one of the final graphs we can look at. Here it is. Now, it's starting to look complicated, but let's just break this down into each little bit. First of all, you're familiar with this type of oscillation, and you're familiar with the fact that there's an envelope over it. In other words, you're familiar that there's a cosine omega t plus epsilon alpha in this case, but in most of these cases, the ones that we've dealt with, we've made that equal to 0, so it's a lot easier to understand. You're happy now with the idea of this exponentiality over the top, the envelope over the top. So there is the function, our general function of this type of oscillation. Now, if our system is, don't worry about these factors here, but let's just, and I should say that this is from Hyperphysics, which is an excellent web page I ought to direct you towards. Just Hyperphysics on Google. I really recommend it. This would be an underdamped situation, because it's bouncing back and forth, just like you saw in the previous video. The critically damped moves to a point of equilibrium as fast as possible, and it couldn't be any faster than that. That is critically damped. The overdamped does move to equilibrium, but just takes a much longer to do it. And of course, if you go any further with the critical damping, you'll get an oscillation the other direction. So you've got to be careful about that. Now, critically damped is its most efficient or quickest movement to the equilibrium position. Underdamped, it takes a long time to hit equilibrium position, and that's overdamped. And underdamped, it oscillates back and forth, back and forth. Good. Now, I think those are all the terminologies that we need to deal with. And in actual fact, what I'll do is I'll leave the forced oscillations, how we drive oscillations, to the next video. But I hope all of that made sense.